Hello. In this video, we will cover tests for paired samples. What are paired samples? In the last two videos, I talked to you about a t-test and an alternative for an independent design. That means the two samples that we wanted to make inference about contained individual data points or samples that were independent of each other. If there's a relationship between the two samples or between data points in the two samples, then this is called a paired design. Examples of a paired design, for example, include measuring your blood pressure before and after you walk up a set of stairs. Let's look at this example. In this example, we have 9 subjects which were supposed to rate their hunger feelings either after a week of taking a placebo drug or a drug which is supposed to reduce the subjective feeling of hunger. These data are paired because the same people took part in both conditions. You can also see that in the way the data is visualized. In an independent sample case, these points would not be connected because there would be no logical way to connect them. They would simply be different persons, some of them assigned to the experimental group that obtained the drug, and others assigned to the placebo group that did not obtain the drug. However, in this case, the researchers chose to use a paired design in which the people first took, for example, the drug for a week, rated their hunger, and then took the placebo for a week and then rated their hunger. Of course, for a proper design, the order in which the drugs are taken would need to be randomized and ideally blinded, as we covered in some of the first lectures. How do we analyze such data? In such data, we are mainly interested in looking at the difference between the two conditions. So the hunger rating here is given on a numerical scale, and you can see the values here. What's interesting for the paired design or for the paired testing scenario is the difference between the two conditions. We observe that the mean difference here is minus 29.6 with a standard deviation of 30.8. What do we do? Let's first look again at the randomization test. The null hypothesis would be hunger when taking the MCPP drug is no different from hunger when taking a placebo. The alternative hypothesis is hunger when taking MCPP is different from hunger when taking the placebo. We have to be careful when we use a randomization test in this scenario. You will remember the randomization test for the independent sample case. In the independent sample case, we simply assigned the subjects randomly to the two groups in the numbers that were present originally. And we did this many times to compute the null distribution empirically. In the case of the paired design, we need to be careful on how exactly we do this randomization. It is important that we simply randomize within subject. So we can swap the placebo and the drug conditions for each subject, but we can only do so within each subject. Otherwise, we destroy the structure of the paired design and compare to a meaningless null distribution. When we do that in this case, we actually find that of all the possible ways to assign the two conditions within the subjects, so it's 2 to the 9 in this case, so 512, only in 12 cases we obtain a mean difference between the two samples that is larger than the one we obtain in our observed data. So for this one here, for example, so this is a randomization of the data, we find that it has a mean of minus 0.7. This again lets us construct a null distribution and compare how likely it is to find data as or more extreme in these randomized samples that has a mean difference as or more extreme in magnitude than the one we observed in the data. We do that, and 500 out of 512 show this, which is equal to a p-value of 0.023. There's also a version of the t-test, which is paired. So we compute we are mainly interested in the differences. So the differences between the sample values of the two samples. For the paired t-test, it is not important whether the two individual samples are normally distributed, but only whether the differences between the two samples are. In our example, these are the differences. It's a dot plot of the differences, and you can see that this is quite clearly shifted away from 0 towards the negative. When we use a QQ plot or a quantile plot, like we discussed in one of the first lectures, we can see that these differences roughly follow a normal distribution because they roughly lie on the main diagonal. The mean difference, of course, is equal to the difference of the means. But this is the statistic that we're interested in. You can also compute the standard error of the mean difference. And now you need to be careful because this is not equal to the standard error of the difference in means that we introduced in one of the last videos. In fact, for the standard error of the difference, of the mean difference, we can in this case use the standard deviation of the differences and divide by the square root of samples. This also allows us to compute a confidence interval, which works analogously to the confidence interval that we covered in the past lectures. The test statistic in our paired design is simply the mean difference divided by the standard error of the mean difference. So to do this for our example, the mean difference is simply the difference in means, which is minus 29.6. The standard error of this difference is the standard deviation of the difference divided by the square root of the number of samples. So in this case, this is 32.8 divided by the square root of 9, which is 3. So the standard error of the difference is 10.9. So the resulting t-statistic is minus 2.96 divided by 10.9, which is equal to minus 2.71. We convert this again to a p-value by computing the probability of observing a test statistic as or more extreme than this, assuming the null hypothesis is true. And this probability in this case is low. It's only 0.027. Thus, in this case, we would reject the null hypothesis that the two means in the two paired samples are equal and assert the alternative hypothesis that there's a significant influence of the drug over the placebo condition. To reiterate, what are the conditions of the test? The differences must be a random sample, and the population distribution of the differences must be normal. So this we tested. We looked at the QQ plot of the differences and asserted it follows a normal distribution at least reasonably. But what we don't need is that the two individual distributions of the sample 1 and sample 2, that these follow a normal distribution. In fact, in one of the cases, we find the sigmoid shape here in the QQ plot, so it clearly does not follow a normal distribution. But yet, the differences do. And this is enough for the paired t-test to be applicable. If you have data where the differences don't follow a normal distribution, you have to resort to a non-parametric alternative, similar to the Wilcoxon-Mann-Whitney test we covered for the independent sample design. Alternatives include, for example, the sign test or the sign rank test. We will not cover these in detail in the lecture, but they are available in all the statistics packages that we use here, and you can also easily read up on them in the book. So why do we do pairing? What is the purpose of pairing? Pairing can help to reduce bias, but more importantly, it increases our precision or can decrease variability. Pairing is always a design choice. It's not an analytic choice. So if you have not collected data in a paired design, you cannot choose to use a paired analysis later. So here you can see an example where we measured a substance, I think the number of E. coli bacteria in a river up and downstream from a sewage plant. And you can see that the data is quite distributed along this axis and along this axis. And by looking only at the differences between the two, so it's kind of perpendicular to that, we increase the precision of our estimates. That is because in different rivers, there's a base rate fluctuation in how much E. coli there is. So there's already variability in this direction. Here's another example that illustrates clearly what the results are of ignoring pairing in a case where it matters. So here we have a scenario where different cheese loaves from a cheddar cheese factory were tested, and their gumminess, so the squishiness, was compared on day 7 and day 30. This was done on 10 different cheeses, and we get these numerical values for the 10 cheeses at these 10 days. Now, there's some variability in the gumminess from cheese to cheese, as there's variability between different people in their base heart rate or their base blood pressure even before walking up a set of stairs. When we compute the differences between the 2 days, we can see that almost all of them are positive. And then we compute the t-statistic, assuming a paired design, so for the paired t-test, which is equal to 4.04. This results in a p-value of 0.003, which is fairly small, so we reject the null hypothesis that the time, so the day on which the gumminess was measured, does not matter for the mean gumminess. Now, if we choose to ignore the pairing, this is something that we can do as an analysis choice in principle, even if it doesn't make much sense if we have a paired design. But contrary to that, we cannot invent pairing if we didn't have it as a design choice, as I said just a few minutes ago. But if in this case we choose to ignore pairing, then we treat these two samples as independent. So we make a dot plot that just simply compares the gumminess on the two days. So we do not subtract out the variability, the baseline variability between the different cheeses. Because we still have this variability in our analysis, the test statistic will only be 1.93 in this case, and the p-value will be larger, equal to 0.072. So with a cutoff of alpha equals 0.05. In this case, we would not assert a significant difference between the gumminess on day 7 and day 30. But because the design of pairing, the paired design, measuring at 2 different time points the exactly same cheeses, allows us to subtract out the baseline variability here, we are able to find the significant difference with a paired test. You will remember that the standard error for the difference in means in the independent sample case included a term both for the standard deviation of the first sample and the standard deviation of the second sample. And this is typically larger than the standard deviation of the differences. And this is because in the pair design, we subtract out some of the baseline variability. What are examples where pair designs matter? Sometimes experiments are done in which similar experimental units can form pairs. So let's say offspring of the same original experimental animal. These could be treated as pairs, or animals raised in the same cage could be treated as pairs if the other experimental conditions allow so. More typically, observational studies in twins, for example, constitute a paired design, or, and I think this is the most common form of a paired design, is repeated measures at 2 or more times in the same individual. So for example, we could have 8 subjects, and in a memorization task, we could ask them to recall a number of words. And once we ask them to recall them briefly after they have memorized them, and then once a bit later. So recall 1 and recall 2. And then we can test whether time matters, so whether over time people forget things in this particular setting. Of course, people have a variable memory performance, and the number of words that they can remember at the baseline condition will vary strikingly between them. Therefore, a pair design here, so asking the same people to recall the words later, helps because it takes out this baseline variability in memory performance. There's also temporal pairing, where we collect for a number of dates upstream and downstream data. Let's say here the number of coliform bacteria in the water of rivers. So by looking at different dates throughout the year and collecting always upstream and downstream data at the same date, we are able to subtract out some of the variation that come from the time of the year. For example, in the summer, coliform bacteria will proliferate more strongly in the warmer waters, when in the winter this may be less of a problem. Today we discussed pairing and paired t-tests. Thank you for your attention.